analog signal. Okay, you're going to sample the signal with a switch, for example. You have a sampler. You switch on and off at certain specific interval. So when you switch it on, you sample it. Okay, let's say it's a 0 time. And then after certain time t, you switch it on again. After certain time t, you switch it on again to t. Okay, so that's you sampling a continuous time signal. And then you output the sample signal as a discrete time signal. For example, let me cut a copy and paste here. So if I delete this, what you're going to see at the output is a discrete time signal. So the discrete time signal are just a sequence of numbers. The input is, let's say, xt. Input is continuous time signal xt. After sampled, you're going to get a discrete time signals xn, which is equals to x n times t. N is the integer and t is a specific interval. So t is the sampling interval. I just put a sampling interval. Then fs is the sampling frequency. So in this case, n is an integer. N is an integer. So you have a continuous time signal xt coming in. Okay. Then you're going to sample that with pt. pt are a series of impulses. Pulses, or we can call this pulse train. You can call this pulse train, like a pulse train. Pulse train. In this pulse train, we'll have a sampling frequency, sorry, a sampling time, Ts. For example, if you call this 0, 0, 1, 2, so the sampling interval, you can call this a sampling time, Ts. And the sampling frequency is 1 over Ts. Okay, you have a pulse coming in, and then this pulse is getting multiplied by an analog signal. Let's say this signal here. Let's assume you have a signal xt. Okay, so when this pulse, okay, when this pulse get multiplied by a signal, what is going to happen? You're going to be sampling the signal. And so on. You're going to sample the signal, and the output is going to be a sampled signal, XPT. You call this XPT. The input here, you call this PT. And the signal, the input signal here is XT, input signal. And the pulse train, you call PT. And the sampled signal, you call XPT. The output signal, you're going to get a discrete time signal. So this is your XPT sampled output. Is the input signal XT multiplied by PT. That's going to give you a sum of sampled signal multiplied by the pulse train. Okay. So for example, when n equals to 0, you're here. When n is equals to 1, you're right here. When n is equals to 2, you're here. That's how it works. Okay. So any questions so far?
No, sir.
Okay. But you know, your problem is very simple. I just give you the background. So the sample signal would look like this. So this is the sampled signal. The sample signal. So the Fourier transform of this signal there's some mathematics involved in the Fourier transform, but we are just using the result. The Fourier transform of XPT, you call this XP omega. And that's going to be equals to 1 over the sampling time summation of k is minus infinity to positive infinity, x minus k omega s. Okay, so omegas of s is going to be the sampling frequency corresponding to the sampling time. Okay, so that's all you need to solve this problem. That's all you need. Let me rewrite this. The Fourier transform of n is equals to minus infinity to positive infinity. Okay, let me just write this. Fourier transform, just the Fourier transform formula. So that's all you need to solve problem number 4. Let's do an example now. Given the signal ft, or you also can call this xt, a signal xt with spectrum. When you mention spectrum, you're talking about the frequency, the Fourier transform xt depicted spectrum, the Fourier transform of xt is x omega. In xt, for example, let's say it's a continuous time signal. But then when you do the Fourier transform, you end up with getting a signal that has a frequency content until 300 pi. So for example, the frequency, this signal consists of various frequency, including DC from 0 up to 300 pi radians per second. See, Fs is 200 hertz. Then the sampling time is 1 over Fs, which is going to be 1 over 200 seconds. The sampling frequency in radians per second is 2 pi f, which is 400 pi rads per second. The Fourier transform of the sampled signal is xp omega, which was given as 1 over ts k is equals to minus infinity x function of omega minus k omega s. Okay. So let's go ahead and write up the equation. The sampling time was found. Ts is 1 over 200. So you're going to get 200 here. 1 over Ts. X omega minus k. Omegas of S is 400. So far, any question?
No, sir.
Okay. So you know that your K varies. Your K varies from minus infinity to positive infinity. We won't be able to sketch until from minus infinity to positive infinity. We just sketch for few integers. Okay, starting from k equal to 0, x omega p becomes 200 x. We could put set k equal to 0. 200 multiplied by, okay. Any question on that? No question? Okay. K. Next, we do this for k is equals to plus minus 1. Because we know, right, k is going from minus infinity to positive infinity. So xp is going to be 200, same 200, but now omega is plus minus 400 because k is plus minus 1. Any question at all?
No, sir.
Okay, good. Next, k is plus minus 2. Omega and k becomes 2. Then this becomes plus minus 800 pi. And k is plus minus 3. (1,200 pi). Amplitude is 1, so 1 times 200 is 200. Okay, and now it's located when omega is 0. When k is plus minus 1, again the amplitude is 200, but it's located at plus minus 400 pi radians per second. So when k is plus minus 2, it's located at plus minus 800 pi. And k is 3, it's located at plus minus 1,200 pi. So we're going to sketch all this. Okay?
Yes, sir.
Okay, the first one, you getting when k is 0, okay, you get this. When k is 0, you get this. Okay, this is when k is 0, okay?
Okay, sir.
The next one, when k is plus minus 1, the same result, right here is 300 pi, right? The same result is now copied to 400 pi. Okay, plus minus 400 pi. The same result is copied to plus minus 400 pi, and k is plus minus 1. Okay, okay so far?
Okay, sir.
Okay, when k is everybody okay? And are you all sure you're all okay?
Okay, sir.
Okay, son, understand.
It's 200. When k is plus minus 2, and now the same thing is shifted by plus minus 800, right? Can you see? At k is plus minus 2. The signals are copied to plus minus 800 pi radians per second. Okay, so 800 is somewhere here. Okay, each division is 100 pi. 100 pi. So similarly on this side, minus 800 pi. So now you copy the spectrum over to plus minus 800 pi. Is that okay so far?
Yes, sir.
Okay, now I can continue to go on, but I'm just doing this for 3 until k is 0. I'm just doing this for k equal to 0. K is equal to 0. Then I'm doing it for k equals to plus minus 1, plus minus 2. Then I'm going to add them up now. Right? I'm going to add them up. So to add them up, what you need to do, probably the best thing to do, you draw some line. Like, you know, okay, draw some line like this. If you have problems seeing it, maybe you want to be, unless you're very sure, maybe you want to draw lines like this. Wherever there's a corner, like for example, what I mean by corner, whenever there's a jump from 0, from 200 to 0 or 0 to 200, so whenever there's a jump, you may want to draw dotted lines. So draw dotted lines. Let's say we drop until here, and then you have also drop as a corner here. So I'm trying to project all these lines. I'm projecting all these lines to draw this, okay? So you drop another line here. It's a corner. So to do this, you must have a squared paper. Definitely you'll be needing this in your assignment. If you draw something without a square paper, you may be getting a bad grade. So when after dropping all these things and then you add them up, let's look at, okay, just look inside here first. Just look inside here first. Maybe I look at a different color. I just look at inside here first. Okay, in this, maybe I drop this line until here so that you can see. So start from the center where I drew. Okay. If you look inside here, in this area, the amplitude of the signal when k is plus minus 2 is 0, right? 0 right here. The amplitude of the signal at plus minus 1 is also 0. The amplitude of the signal when k is equal to 0 is 200. Okay, so that's how we get 200. Yeah. Clear that part?
Clear, sir.
Can everyone see that?
Yes, sir.
Yes, sir.
Okay, now you're done with this. To avoid confusion, remove it. After you already sketched it, maybe what I'm going to do, maybe I will just delete this first. Okay, so I've drawn an amplitude 200 because of this. 200 plus 0 is 200, correct? Next, look at this. Instead of scratching, let's put a dash line. Look at this area here. Okay, then you see in this area zone, 0 amplitude plus 200 and then plus 200 is going to give you 400, correct? $400. Do everyone agree with that?
Agree, sir.
Okay, how about other guys?
Agree, sir.
Agree, sir.
To understand,
Agree, sir.
Agree, sir.
you have to do all these things before you can sketch it, right? Okay, now you look at the next one. Okay, so you're already done with this zone. You're already done with this zone. Now you just look at this zone. Just look at the positive side first, on the positive frequency. Okay. Yeah, 0 amplitude. Right, yes, 200. 0 plus 200 is 200, 0 amplitude. So the net is 200. Okay, that's how you do it. I think if you know, you don't have to really repeat this anymore because you know the pattern. You can, if you can do this for 3 of them, is sufficient, is enough. Then after that, you just repeat the pattern. It's continuing to go on. So on this side, you just flip it around the vertical axis. You don't have to go through that calculation again because on the right, on the negative side, is just a carbon copy of the right side. Maybe this way is better. You know, earlier on when I drew this in different colors, they overlapped and camouflaged the other colors. I'm glad somebody asked me to do this again so that other students can see this. So that is the amplitude spectrum. That is the amplitude spectrum for the sampling frequency. When the sampling frequency is how many hertz? 200 hertz. 200 hertz. Okay, now is this clear?
Yes.
Yes, sir.
Okay, thanks. Sorry. Now let's do for sampling frequency 300 hertz. And summation of k is from minus infinity to positive infinity. And then xp omega minus k. Omega is the same thing before, but then we have to calculate sampling frequency. Sampling time is 1 over 300. Omegas of s is 2 pi over t, which is 2 pi over 300. T is 1 over 300, right? So omegas of s is 600 pi, isn't it? So equation is going to be xp omega is 1 over 300. Okay, 1 over, it's going to be 300 here. Omegas of s is 600 pi. So you repeat the same thing again. When k is equal to 0, When k is equals to plus minus 1, sorry, 600 times pi times 2 is plus minus 1200 pi. Okay, maybe I will draw this again like earlier on. Okay. Same as before, when k is 0. Amplitude, when k is equal to 0, plus minus, amplitude is 300. Same as before, plus minus 300, right? When k is equal to 0. When k is plus minus 1, so the signal is going to be copied to plus minus 600. What happened here? Some aliens operating my stuff without my permission. Okay.
Mr. Walter Go, sir.
Huh?
Walter Go, alien, sir.
Alien. Please catch it.
Yes, sir. It's an alien.
Thank you. So now, when k is plus minus 1, you're going to be copying it at plus minus 600 pi. So don't forget, so, you know, I'm happy with the drawing 2 of them, because the next one I'm going to draw is going to be quite easy also, at plus minus 1200 pi. 600, 600, somewhere here, right? Okay. If I add them all up, you can see it's going to be a straight line. Right. You can see right here, if you draw those dot line, So in this area, the amplitude is 300 pi. So if you drop the dotted line here, in this region, it's also 300 pi. If you drop a line here, like in this region, the only amplitude is 300. So that's why I'm getting 300 pi. The next one here, also 300. Okay, 0 plus 300 plus 0 is 300. The next one, you also write 300 plus 0 is 300. So if you repeat this for k up to plus minus infinity, you're going to get a band. Any question on this? Amplitude spectrum at when Fs is, what was Fs? Fs is
300 hertz.
yes, 300 hertz. Okay. Any question on this? Everybody understand this? Please draw it neatly. So I'll do one more frequency.
Sir,
Yeah,
will you upload this in YouTube?
yes, of course.
Okay, sir. Thank you.
Since you requested, we'll upload it because you are the king around here. You're the most important person, of course. So one more frequency, repeat. I'm uploading every lecture, Mr. Arun. Don't you know that?
Yes, yes, I know, sir.
Repeat when somebody got the mic on, I think. So omegas of S is 2 pi Fs, 800 pi, and then sampling interval seconds. So I'm going to go a little bit quicker here. Is 400, same formula. So when k is equal to 0, xp omega is 400 when k is equals to plus minus, when k is equals to plus minus 1, when k is equals to plus minus 2, okay, let's, any question on this? Any question?
No.
Sir.
Okay, let's plot. and case is 0. So that's when case is 0. K is plus minus 2.
Sir,
Yes, sir.
the 300 won't be 400, sir.
300.
The 300, negative 300 pi, right?
Yeah.
For everything, it will be 300 only, sir.
You mean this is the original spectrum that was given to you. This
Oh.
originally given to you.
So
So this is the
okay.
the bandwidth is fixed. So this is determining the bandwidth. So you just shifting it at different to different. You just copying this spectrum to different locations.
Okay, sir.
This is what you're doing when you're multiplying two signals. This is communication theory. You guys studied modulation, right? Modulation in communication theory. Did you all study?
Yes, sir.
This is what is happening when you modulate a signal. So still, so this is going to be, this amplitude changes, but still the same thing. You asked Mr. Arun Raj asked a very good question. The same thing, you know, like here is 300, right? Right or not? So 300, so 800 plus 300. 800 plus 300, this is going to be 1,000. How much?
1100.
Yes. But we we didn't put, we just put the center frequency. So here is going to be 500. Plus minus, so it's just a carbon copy here on the side. It's going to be minus 500 pi, and then minus 1100 pi. So for this is when k is equals to plus and minus 1. Next one, when k is plus minus 2, and k is plus minus 2, maybe there's no place to draw this. Okay, let me move it a little bit. But actually 2 is sufficient, I think, in this case. We want to 3, so the k is plus minus 2. You're going to end up 1600 plus minus 1600. which is going to go away in case plus minus 2, the amplitude spectrum gets shifted to plus minus 1600 pi. So like 100, somewhere here. Okay, don't have to go any further. I think it's enough here. Well, we had all that. You just drop these lines here. You can see that there's nothing in this area except this amplitude spectrum, which is 400 minus 300 pi to 400 pi. Sorry, minus 300 pi to 300 pi. Similarly, if you drop this line, you can see that similarly, you do two of them is sufficient to determine the pattern of the others. It will continue to go up to negative infinity. So on this side is just the carbon copy. Maybe I want to draw this thicker. Okay, any question? You guys see this? Can you guys see? Any questions?
Yes, sir. No question.
Okay, that's important thing that I would like to point out the reason for doing this. You can see this is the spectrum. This is the input signal, right or not? Okay, this is a signal that's coming in, isn't it? Okay, all agree? And then you sample the signal at the output. You also should be able to recover the same bandwidth, correct? So when your sampling frequency is, when your sampling frequency is when your sampling frequency is 200 hertz at the output, this is what you're getting, right? This is what you're getting. Let's say if I use a filter to filter from plus minus 300 pi, if I use a filter to try to recover my signal, as you can see, it's no good. The original signal, right? You can see the amplitude is not consistent because of overlap. Amplitude is higher in this frequency range and is lower here, and this lower and is higher. It's not a good sampling frequency. Okay, you look at the next sampling frequency. If I increase the sampling frequency to 300, what happens? Let's say if I use a filter to try to recover this, if I use a filter, try to recover this amplitude, I might be able to recover, but still you're on the borderline. You see, on the borderline. Still at plus minus 300 pi right here. But if you increase the sampling frequency to 400 hertz, is it 400 hertz that we increase the sampling frequency? Okay, when we increase the sampling frequency to 400 hertz, and you see at the output, output, you should be able to filter this very nice. You see, you should be able to filter this out without disturbance from the adjacent spectrum. Right, so this is called, this is the reason why we want to have the sampling frequency. We want to have the sampling frequency at least 2 times bigger than. So the moral of this exercise is if sampling frequency is, for example, if omegas of s is greater than 2 times the maximum signal frequency, no aliasing I am not sure if I'm spelling this correctly. No aliasing. Aliasing means, this is what aliasing is. See right here. This is what aliasing is. Distorted. No aliasing. So if you have your sampling frequency is twice bigger than the signal frequency. Okay. Twice, more than twice bigger. If twice bigger, Okay, it's just nice, but still at the borderline. But it is bigger than twice is much better because you have a clearance here for filtering. No lysing occurs. And we reconstruct okay, if sampling frequency is equal or less than twice the maximum frequency, lysing occurs. From xn. Xn is the sampled signal in general. Okay, and this is quite easy, in the exam, all you have to do, you have to know this formula. Make sure you have to know if this is in the exam. If it comes out in the exam, all you have to know is this formula here. And then make sure you show your work in detail. So let me, do you guys have any question?
No, sir.
So let me go and quickly do another question here, so that will help you to do the assignment. Again, JJ was asking, I'm sure most of you never seen this type of questions before. So let me quickly. The differential equation given. I want to do a Laplace transform on this. It's going to give you s squared ys plus 12 s ys plus 20 ys. This is equals to 3xs. Then you solve for ys. Sorry, please alter this. This is 30. I put 3 here. It's supposed to be 30.
Sir,
Yeah.
you using this is Fourier transform, am I right?
But using what?
Is this Fourier transform or using Laplace transform, sir?
Laplace transform.
But Laplace transform, we have the y bracket 0, am I right? If for the dy dt.
Yeah, that's so you use that only when the initial condition is given.
Oh, if the initial condition is not given, we just consider as 0. Is it?
Yes.
Okay, sir.
Yeah. Yes.
Okay, sir. Okay, sir.
Okay. So do you guys understand what he's asking, right?
Yes, sir.
He's asking if this is the Laplace transform of this is, you know, s squared ys, and then you will have 0 and minus y0. So if the initial condition is not given, you just ignore this. All right. A good question. So, right, the frequency response using phasor analysis, the frequency response, the transfer function is ys this is if you factor this, you don't have to, but if you like, you can. Okay, this is the transfer function. This is the, you have a system and you have h of s. This transfer function is just like a, sorry, this is x of s. Input in Laplace domain, in frequency domain, time domain is xt, in time domain is yt. Okay, this is the system and this is a frequency response. It's a frequency response. And you're told to find yt given input. Okay. All right, using phasor analysis. Phasor, you know, right, phasor? Okay, now you can see the input as the DC plus AC. DC omega 0. In this case, for Laplace, we don't talk about omega. We're talking S. It's a complex frequency. Right? Here the frequency is J20 for AC. Any question? Any question?
No, sir.
All right, to find the output for the DC input, what we do, we find the output. So we have the input DC, then we find what is the output DC. Input DC, output DC is what? Input AC, output AC is what? Once you found them, you just add them up. Total output is AC output, DC plus AC. That's what we are going to do. So now look at DC. And DC, S equal to 0, right? For DC. So we plug that into the transfer function. We find out that, plug that into the transfer function with s equal to 0. So it's going to give you 30 over 0 plus 2, 0 plus 10. It's going to be 30 over 21.5. All right. Just for the DC part. For the DC part. For the DC part, what will be the output for the DC part? Which is a x as input multiplied by the transfer function or gain, which will be the amplitude in time domain multiplied by the amplitude of the this is a ht in time domain. Okay, the input, as you know, is 5. Input is 5. Output is, you just calculated that to be 1.5, which is 7.5. Okay, is that clear? So you already found the output for the DC part. For DC only. For DC part only. Is that clear, guys?
Yes, sir.
Yes, sir.
Okay, for
Yes,
AC part, yes.
Clear, it's clear.
Okay. AC part. So we have here J20. The frequency can be found from here. This is the frequency. Right here, this is omega. Omega is 20, which is responsible for the imaginary part. Just plug that into the transfer function equation and evaluate that. I factorized this earlier so that it'll be easier to do that. If you using your hand to do it or calculator, six, 7 at a minus 147 degrees. So you have to convert this into polar. So now the output, the AC output, due to the frequency omega is 20, is input function of J20 multiplied by the transfer function at J20. So we already know our input is given earlier. You look, our input is given here input. There's no phase shift. For the input, there's no phase shift. Amplitude is 6, but there's no phase shift. 0 phase shift. Amplitude is 6. 0 phase shift. Multiplied by the transfer function we just evaluated, which is 0.0667 at minus 147 degrees. We multiply them out, you're going to get minus 147 degrees. Is there any question so far?
sir.
By superposition, AC can be added to DC. The output in time domain is the DC that was obtained, DC output plus the AC output in time domain. The DC output we found out it to be 7.5 plus the AC, which is 0.4. Okay, now I'm going to convert this to time domain. 0.4, you can use sine or cosine, but if you go back to your input was in sine, right? So input was in sine. So you use sine, the output also to be compatible. If you use cosine, then you'll be, you are shifting your answer by 90 degrees. That will be an error. So you use the same sign in omega. Omega frequency is still the same, right? Frequency is still the same, which is 20t minus 147 degrees. The output is a phase shift. The output at a phase shift. Amplitude 0.4. Frequency. So that's the output. We're running out of time. So next question is for the part B. Let's say now let's say your xt is a step function. Five at t equals to greater than 0, 0 for t less than 0. The step function. Now your input is different. Earlier on, we never talked about the input because we were just looking at, we were given an input. But now, sorry, we had an input earlier, but now we have a different input. Our input earlier was a DC plus AC. Right now, our input is a step function. The Laplace transform of a step. So this is 5. Okay, this is 5 ut. The Laplace transform of 5 ut is 5 over s. Go ahead and now your y, you're going to find out what is your output when the input is a step function with an amplitude 5. So use the same equation you had earlier, but now your input is a step function. Okay, so from here you know what to do. From here you know what to do. G, what we do from here to find yt?
Do a partial fraction, sir.
Fantastic. Yes, good job. After partial fraction, what we do, Kavin? Kavin,
Find s equals to 0, s equals to 1.
so then you do partial fraction and then you eliminate and then you'll find A, B, C. Okay, let me see. Then you set this equals to A over S plus 2 plus B over S plus 10 plus C over S, right? Right? By elimination, you guys go ahead and try this. We can continue. What I got for A is minus 9.375, B 1.875, C is 7.5, and then YS So you have one assignment question, pretty much the same as this. Kavin, did you go to toilet today?
No,
Sir,
not
today is his birthday, sir.
What's up? I didn't ask anything funny, man. I'm just taking care of your well-being.
yes, sir, yes.
Okay, so the Laplace transform of this is going to be like maybe somewhere, I'm not sure if I'm doing this right, but the procedure is right. Check the numbers. So this answer is not in Can I upload
sir.
this video now?
Can, sir, can, sir.
Can, sir.